I was scrolling through a series of tech forums earlier this week, and the name DeepSeek was just everywhere. It felt like watching a magic trick where the magician pulls a rabbit out of a hat, except the hat is a relatively small Chinese startup, and the rabbit is an AI model that rivals GPT-4 for a fraction of the cost. People were genuinely baffled. I saw one developer post a thread essentially saying, "There's no way they did this with the hardware they're allowed to have. The math just doesn't add up." That's when the whispers turned into a full-blown accusation. Suddenly, the narrative shifted from efficient engineering to international scandal. The word on the street was that DeepSeek had somehow gotten its hands on the forbidden fruit, NVIDIA's Blackwell B200 chips, through illegal back-channel smuggling operations. The theory was simple. The only way to beat the West is to steal the West's best tools. It painted a picture of a desperate race to bypass U.S. export bans, complete with secret server farms and shadowy middlemen. But then, on December 14th, NVIDIA itself stepped into the fray and did something unexpected. They flatly denied it. They confirmed that the illegal chips weren't there. This is where the story takes a much more unsettling turn for Silicon Valley. If the smuggled chips aren't there, but the performance is real, it leaves us with a realization that is far more terrifying to U.S. regulators than a few crates of leaked hardware. The panic we're seeing right now isn't actually about illegal chips. It's the sudden, cold realization that the multi-billion-dollar hardware moat the U.S. has been building might just be a sandcastle in the face of a superior algorithm. If you can't stop them with a blockade, how do you stop them at all? That opening really sets the stage perfectly for what we're diving into today. This is a story about the intersection of, well, geopolitics and pure mathematics. The core conflict is that the narrative shifted from this idea of hardware theft to the undeniable reality of a superior software and algorithmic architecture. Our mission is to take the DeepSeek V3 technical report and just unpack it completely. We need to understand precisely how they achieve state-of-the-art performance, comparable to the absolute industry leaders like GPT-4 and Claude, with the dramatically reduced hardware dependency, mostly utilizing restricted, older generation chips like the H800. If the goal of trade restrictions was to enforce a hardware moat, DeepSeek just show how porous that defense really is through sheer mathematical ingenuity and engineering prowess.
That narrative of algorithmic supremacy over hardware brute force is exactly the challenge we face right now. It is deeply unsettling for the established frontier labs because their business model relied on the concept of scaling laws. Spend more money, buy more chips, get a better model. DeepSeek V3 fundamentally disrupts that entire idea. We have to start by validating that core performance claim, because if the results weren't truly exceptional, the panic wouldn't exist. The unsettling truth is that DeepSeek V3's chat version is achieving performance comparable to leading closed-source models that the industry has spent fortunes developing, like GPT-4o 0513 and Claude 3.5 Sonnet 122.
And the performance parity alone is remarkable, but what makes this a truly disruptive event, and what fueled that initial panic you were talking about, is the minuscule economical cost required to reach that level.
That's where the numbers stop being about computer science and start being about macroeconomics. Let's look at the financial metrics that fundamentally shock the industry. Based on the technical report, the total training cost for DeepSeek V3 was estimated at only $5.576 million, and that covered everything. The massive pre-training stage, the subsequent context extension, and the highly specialized post-training refinement.
$5.5 million. That's what some of the frontier labs in Silicon Valley spend on their office snacks, their launch parties, or a single round of seed funding. I mean, it is an insignificant amount of money in the world of trillion parameter models. How does that translate into the actual computational effort required?
It translates to an astonishing efficiency. The total computational budget came out to 2.78 million H800 GPU hours. The vast majority of that, 2.6 million hours, went into the initial pre-training stage. Context extension required about 119,000 hours, and post-training required a tiny 5,000 hours. And this is all based on a typical H800 rental assumption of about $2 per GPU hour.
So we're talking about a model that costs the equivalent of a mid-sized apartment complex in a major U.S. city to train. Yet it performs like $1 billion supercomputer.
That's the magnitude of the difference. They cite a key efficiency metric. Training on each trillion tokens required only 180,000 H800 GPU hours. If you ran that on their full 2048 H800 cluster, it would take just 3.7 days. This level of economic efficiency is the clearest indicator that they were not relying on traditional scaling laws. They were doing something fundamentally different than just scaling up transformer blocks. They were co-designing the algorithm with the hardware limitations in mind.
Okay, let's get granular on the performance, because the low dollar amount only matters if the output is truly top tier. Where did DeepSeek V3 specifically excel, beyond just being comparable in general chat?
DeepSeek established dominance in areas requiring complex, high-level reasoning and technical expertise. The DeepSeek V3 base model is currently recognized as the strongest open-source model available, full stop. Let's look at a concrete example. GPQA Diamond. This is a very difficult specialized test designed to evaluate PhD-level knowledge and reasoning ability, often involving complex scientific or technical arguments.
It's the deep end of the pool.
It is. On GPQA Diamond, DeepSeek V3 achieves 59.1% pass at 1. To contextualize this, it ranks just behind Claude 3.5 Sonnet, which scored 65%. But critically, it substantially outperforms GPT-4o, which scored 49.9%. That's a nearly 10 percentage point lead over one of the most highly touted frontier models.
Wait, let me make sure I heard that right. On a highly complex, difficult scientific reasoning task designed to push the limits of comprehension, the model trained for $5.5 million beat a top-tier proprietary model by a significant margin. That is a stunning validation of their efficiency.
And their dominance is even clearer in specialized technical domains like math and coding, which are often the bottlenecks for general LLMs. DeepSeek V3 achieves state-of-the-art performance among non-long chain of thought models in math. For example, on the challenging Math 500 benchmark, which requires step-by-step problem solving, it scored 90.2%. That is a massive margin over the second-best model in the open-source category, Win2.572b, which scored 80%.
An absolute score increase of 10 points on a hard math test like that is an eternity in this field. It suggests DeepSeek has a fundamental underlying superiority in its ability to follow logical steps.
Similarly, in coding, it was the top-performing model on Live Code Bench, Human Evil, Mole, and Codeforces, achieving a 51.6 percentile on the latter. This solidifies its position as the leading model in technically demanding domains, which suggests the architectural choices they made specifically benefited structured, sequential reasoning.
And we also see multilingual strength, which reflects their strategic resource allocation, making this a true global competitor.
Yes, it's an interesting trade-off they made. Due to a deliberate token allocation strategy, DeepSeek V3 trails behind closed-source models in English factual knowledge as they decided to prioritize training resources. However, it surpasses them in Chinese factual knowledge. On C-Simple QA, a Chinese factual knowledge benchmark, DeepSeek V3 scores 64.8% compared to GPT-4o's 59.3%. This is a direct consequence of allocating more training tokens to Chinese knowledge resources. It's a demonstration of targeted efficiency meeting domain superiority. They didn't try to be best at everything, but best where it mattered most for their intended market, and they achieved that superiority cost-effectively.
Okay, let's unpack this. If the training cost is radically low and the performance is this high, particularly in hard technical areas, the hardware itself clearly wasn't the bottleneck. The moat truly must be in the software, the algorithmic architecture, and the engineering framework. The question then becomes, what are those specific innovations that allowed them to neutralize the hardware restrictions imposed by relying on the H800 instead of the latest unrestricted chips?
We need to start with the foundation decision, which is the architectural choice. The mixture of experts or MOE design. DeepSeek V3 utilized a MOE architecture with a massive 671 billion total parameters. This is the capacity of the model, all the knowledge it potentially holds. But here's the key difference and the source of efficiency. During inference, only 37 billion parameters are actually activated.
So they have the knowledge capacity of a giant, almost trillion parameter model, but the operational cost and latency of a model that's barely 1/15 of that size.
That's exactly right. For every single token generated, you only run a small, dedicated subset of the total model. This inherent sparsity is their first line of efficiency. But MOE itself isn't new. The challenge with MOE has always been optimizing it to work perfectly. DeepSeek introduced 3 main architectural innovations to make this MOE architecture work flawlessly, and they are what truly define their algorithmic moat.
Let's start with the one that deals with the fundamental flaw of MOE, the load balancing problem.
The first innovation is revolutionary for MOE training, the auxiliary loss-free load balancing strategy.
Traditionally, when you use MOE, the biggest operational problem is that some expert networks get overloaded while others remain idle. This creates inefficiency and can lead to routing collapse, where the router just learns to use the same few popular experts all the time. How is that typically solved in other models?
Conventional methods rely on an auxiliary loss term, a performance penalty, to encourage a balanced expert load. You essentially tell the model, if you don't spread the tokens around evenly, I'm going to hurt your overall training loss. End quote. But that penalty can, ironically, impair the model's overall performance if it's too aggressively applied. It forces a rigid balance that prevents deep specialization. DeepSeek V3 engineered a solution that eliminates the need for that performance-impairing auxiliary loss, hence the auxiliary loss-free name.
How do they force balance without applying a penalty to the main training objective?
They created a self-adjusting governor. They introduce a dynamic bias term for each expert. This bias term is added only when the router is deciding which experts a token should be sent to. This pushes certain tokens towards less busy experts during the selection process. Crucially, this bias term is not applied when calculating the final gating value that determines the expert's output contribution.
So the bias influences the selection, but not the final output quality. It's a pure traffic cop rather than a sensor.
Precisely. The real intelligence comes from how they dynamically adjust that bias during training. At the end of each training step, they monitor the expert load across the whole batch of data. If an expert is overloaded, its bias term is dynamically decreased, making it harder to select next time. If it's underloaded, the bias is increased, making it more attractive. This is a batch-wise mechanism, not a sequence-wise constraint.
What's the practical advantage of making the balancing flexible and batch-wise instead of a rigid per-sequence constraint?
The flexibility allows experts to exhibit greater specialization patterns across different domains. Think about it. A rigid penalty forces every expert to be a generalist. DeepSeek's method allows the experts to naturally divide the labor based on content. For instance, in their testing on the Pile dataset, they saw experts focused intensely on GitHub code, while others focused specifically on Wikipedia articles and others on DM mathematics. They showed much cleaner specialization boundaries compared to a model using traditional auxiliary loss.
So this isn't just about saving money, it's about achieving a level of specialization that brute force dense models simply can't match. The architectural freedom means the model can allocate specialized knowledge more effectively without having to compromise performance just to satisfy a rigid load constraint.
And ablation studies confirm this. The auxiliary loss-free strategy consistently achieved better model performance across the board. That is the first pillar of their algorithmic moat.
That makes perfect sense. Okay, what's the second major breakthrough, which deals with speed?
That would be multi-token prediction, or MTP, which aims to boost training performance and, critically, inference speed. The concept is that the model predicts the immediate next token, which is standard, and simultaneously predicts several additional subsequent tokens sequentially. This MTP acts as an auxiliary training objective.
So they are training the model to think ahead multiple steps. That should make the primary model better, but also give them something useful for generating text quickly.
Exactly. The training benefit is proven. Ablation studies clearly demonstrated that introducing MTP consistently enhances performance across critical benchmarks like human evil for coding and math. It forces the model to learn longer-term dependencies, but the genius lies in their repurposing of this capability for inference acceleration.
Wait, isn't that essentially the core idea behind speculative decoding? They've managed to build that acceleration directly into the fundamental training architecture.
It is speculative decoding, but built in and highly efficient. When the MTP modules are used for speculative decoding during inference, they predict multiple subsequent tokens very quickly, which are then verified by the main, slower model. The acceptance rate of the second predicted token, the one generated speculatively, is remarkably high, sitting between 85% and 90% across various generation topics. This minimizes the need to recalculate.
And what's the real-world impact on speed?
This translates directly to a significantly improved decoding speed, 1.8 times tokens per second, almost doubling the speed just from an architectural change, without relying on faster hardware. It's computational efficiency realized through smarter prediction.
That's truly phenomenal. Okay, tell us about the third innovation, which focuses on memory consumption. That's a huge constraint when you're dealing with long contexts on limited hardware.
That's the multi-head latent attention, or MLA. The primary goal here is to reduce the key value, or KV, cache memory footprint during inference. To understand why this is so important, you have to realize that when an LLM generates text, it has to store all the intermediate computations, the keys and values for the previous token, so it can pay attention to them in the future. This KV cache is a major memory constraint, especially for long context windows, where memory usage balloons and often hits the limits of the HBM, the high bandwidth memory, on the GPU.
So the biggest bottleneck for using a massive model with a massive context window isn't the processing speed. but literally running out of memory to store the conversation history.
Precisely. DeepSeek V3 is a massive model, but it needed to handle context windows up to 128K tokens. How did they shrink the cache size without losing performance? MLA introduces a mechanism using low-rank joint compression on the attention keys and values. They take those keys and values and project them into a much smaller, compressed, latent vector.
So instead of caching the full high-dimensional memory of the past conversation, they cache a small, efficient summary of it, like a compressed ZIP file.
Exactly. During generation, only this compressed latent vector needs to be cached. This results in significantly reduced KV cache size while maintaining performance comparable to standard multi-head attention. This memory efficiency is critical because it frees up the finite high bandwidth memory on the restricted H800 chips. It allows DeepSeek to run massive models and long contexts more affordably and on the hardware they have available. They are circumventing the memory limitation of the H800 through software compression.
Here's where it gets really interesting. These algorithmic innovations, the loss-free MOE, the MTP acceleration, and the MLA memory compression, prove that the superiority lies in the mathematics. But mathematical breakthroughs still have to run on real metal. DeepSeek was constrained to use clusters of NVIDIA H800 GPUs. These chips are explicitly hobbled by U.S. government designed to be less performant than the flagship chips available elsewhere. The question is, how did they take these superior algorithms and force the restricted hardware to execute them at peak efficiency?
This moves us firmly into the realm of extreme efficiency engineering, specifically the custom framework they built called HAILM. We need to look at two main engineering pillars. First, their work in low-precision training, and second, their communication optimization across a huge cluster.
Let's start with low-precision training. They pioneered a comprehensive framework utilizing the FP8 mixed precision training format.
FP8, or 8-bit floating point, is notoriously tricky to train large models with because of the reduced dynamic range and limited precision. If you lose too much accuracy during training, the model collapses. DeepSeek V3 is the first to successfully validate FP8 feasibility on an extremely large-scale model like this, showing that the relative loss error remained below 0.25% compared to the higher precision BF16 training. This was a critical validation.
The main challenge with 8-bit training is dealing with outliers, those extreme values in the data that fall outside the tiny 8-bit range, causing catastrophic overflow and destroying the training process. How did they mitigate those?
They employed two critical mitigation strategies. Strategy A was fine-grained quantization. Instead of applying scaling factors broadly across the entire tensor, they applied scaling at a much more granular microscopic level, on a tile-by-tile basis for activations, and a block-by-block basis for weights.
So they are microscaling the formats, essentially isolating outliers to tiny controllable groups so that one huge data spike doesn't destroy the quantization of the entire batch.
Exactly. This fine-grained approach ensures the quantization process adapts better to localized outliers. This level of granularity minimized the information loss associated with the lower precision. They noted that this strategy is so effective that it should be built into future hardware, suggesting that their software optimization is now defining the future requirements for AI chip design.
That's a powerful statement about their ingenuity. Now, strategy B addresses a known architectural limitation of the H800 itself regarding how it performs low-precision math.
Yes, this is where they had to fight the core design of the H800. The key problem, exposed only when pushing the limits of FP8 training, is that the FP8 GEMM accumulation precision on the H800 tensor cores only retains about 14 bits of precision. This is significantly lower than the standard 32-bit accumulation. When you have billions of parameters and the inner dimension of your matrix multiply gets large, this limited precision quickly leads to error accumulation that can destabilize the training.
So the core hardware designed for speed wasn't precise enough to do the required low-precision math accurately for a model of this size. That would be a deal breaker for stable large-scale training. What was the compromise?
It forced a complex workaround: promotion to CUDA cores. The tensor cores execute the bulk of the speed-critical matrix math. DeepSeek engineers figured out that during this execution, at frequent intervals, after every small accumulation step, they had to pause the process. The partial results were copied out of the high-speed, limited-precision tensor cores and sent to the full-precision registers on the slower CUDA cores, the part of the chip usually reserved for general computation. Full 32-bit precision accumulation was performed there, guaranteeing accuracy, and then the results were set back for the next round of tensor core calculation.
They are essentially fighting the hardware limitation by outsourcing the final addition to a higher precision, albeit slower, part of the chip architecture at frequent measured intervals. They refer to this explicitly as a compromise due to the Hopper architecture's deficiency. But didn't that significantly undermine the tensor core speed advantage?
That is the trade-off they had to accept. It adds overhead, but it was a brilliant and necessary compromise that achieved successful FP8 training at enormous scale. It proves the viability of low-precision training even when the underlying hardware isn't perfectly optimized for it. They chose stability and accuracy over raw, unstable speed, yet still maintained a massive overall efficiency lead over higher precision training methods.
Moving to the second pillar of engineering, optimizing communication within their cluster. They trained DeepSeek V3 on a massive cluster of 2048 NVIDIA H800 GPUs. When you spread a mixture of experts model across multiple nodes, each node being a group of GPUs, the communication overhead, particularly the all-to-all exchange needed for MoE, becomes monstrous.
Absolutely. They utilize 16-way pipeline parallelism and 64-way expert parallelism, which spanned 8 separate server nodes. The problem was that the cross-node expert parallelism introduced such heavy communication overhead that their computation-to-communication ratio was abysmal, sitting at roughly 1:1. Half your expensive training time is spent waiting for data to travel across the network.
That's where the DualPipe algorithm comes in to wrestle back that wasted time.
DualPipe is their specialized pipeline parallelism algorithm. It was designed to minimize pipeline bubbles moments, where GPUs sit idle waiting for data and, crucially, achieve full computation-communication overlap. The core idea is to rearrange the sequence of operations and carefully overlap the forward pass computation of one small chunk of data with the communication of the next chunk of data.
Wait, so this means they effectively eliminated the network latency barrier, turning a crippling inefficiency into a zero-cost operation on the clock. That is the real secret weapon for achieving their low training cost.
It is staggering efficiency. They fully hid the heavy all-to-all communication required for MoE and the standard pipeline parallelism communication during the execution of the actual math. This was supported by custom-built cross-node all-to-all communication kernels, co-designed specifically with the MoE algorithm and the cluster's topology in mind.
And the cluster topology is key, right? Within a single server rack, you use the super-fast NVLink. But across server racks, across nodes, they have to rely on the slower InfiniBand, or IB, interconnects. That difference in speed is their biggest vulnerability.
That's where the precise engineering came in. They engineered a mechanism to limit each token dispatch to, at most, 4 nodes, specifically to reduce the slower InfiniBand traffic. Tokens are first transferred via IB to the GPUs with the same index on the target nodes, and then instantly forwarded via the faster NVLink to the specific GPU hosting the target expert. By overlapping these two different speed communication streams, IB and NVLink, they could theoretically scale up to 13 routed experts without incurring additional communication overhead. In practice, they used 8 routed experts, but the key is that the communication time was essentially eliminated from the overall training time.
They pushed the restricted H800 cluster to its absolute physical limit, even down to which part of the chip was doing the calculation and which network link the data was traveling on. And in doing so, they provided a direct assessment of the hardware's weaknesses.
They absolutely did. The technical report included a set of hardware design suggestions, which amounts to an engineering wish list for future chips, telling NVIDIA exactly where the H800 was deficient.
What were their top demands? What did the H800 lack that forced their compromises?
First, related to their FP8 precision compromise, they noted the critical need for higher FP8 GMM accumulation precision directly in the tensor cores. They want to avoid the time-consuming workaround of promoting results to the CEDX. They want the high-speed core to be accurate enough on its own.
And second, relating to their fine-grained quantization breakthrough in Strategy A.
They identified a need for native hardware support for tile and blockwise quantization. If the tensor cores could natively handle the precise, fine-grained scaling factors, it would eliminate the frequent, inefficient data movements between the tensor cores and the CAA cores required to apply those fine-grained scaling factors. It would remove another bottleneck they had to engineer around.
And the third major suggestion addressed the DualPipe solution.
Yes. They pointed out that dedicated hardware components for communication tasks are sorely needed. Currently, the H800 wastes a significant number of its streaming multiprocessors, which are designed for computation on handling network communication. Dedicated communication hardware would free up those compute resources, maximizing throughput. Their innovations were so specific they acted as a direct design spec for what the Blackwell series should have done to eliminate these specific bottlenecks.
This brings us to the strategic implications. If DeepSeek V3 can achieve state-of-the-art results for $5.5 million using restricted hardware and software ingenuity, the U.S. trade restrictions didn't just fail to stop progress. They actively accelerated it by forcing a focus on algorithmic efficiency over hardware brute force.
That's the core strategic implication we can't ignore. The crisis of restricted hardware access accelerates the push for algorithmic sovereignty. The DeepSeek success demonstrates that computational power can be manufactured through optimized software rather than solely purchased via massive brute force hardware procurement. The policy essentially created an involuntary incubator for high-efficiency domestic innovation.
We even saw NVIDIA CEO Jensen Huang publicly acknowledge this policy was a failure. That's a strong statement coming from the company that essentially controls the core resource the policy was meant to protect.
Huang's feedback was detailed and blunt. He revealed that since the export controls began, NVIDIA's market share in China dropped sharply, from a near monopoly of 95% down to 50%. Furthermore, the firm faced a significant financial hit, noting a $5.5 billion write-down to its inventory due to new regulations requiring licenses to sell advanced AI chips to China. The economic cost of the policy to the leading chip maker was immense.
And beyond the financial cost, what did he say about the long-term strategic impact?
He stated clearly that the export controls gave local Chinese companies the spirit, the energy, and the government support to accelerate their development. The ban acted as a powerful motivator, driving investment and focusing talent on a single critical problem: how to achieve world-class AI without world-class unrestricted hardware. It forced an engineering solution to a geopolitical problem.
This blockading action directly spurred the rise of domestic competition that can operate entirely outside the U.S.-led supply chain.
Absolutely. We see this with Huawei, whose Ascend 910C chip technology and Cloud Matrix cluster are now directly competing with NVIDIA's high-end offerings like Grace Blackwell and H200, but designed to operate within a domestic ecosystem. We also see companies like iFlytek, whose Spark X1 model is explicitly trained entirely on domestic computational infrastructure, proving the feasibility of non-NVIDIA reliance. This isn't just about catching up, it's about decoupling.
This entire development points to a philosophical shift, moving away from the silicon supremacy argument, that he who controls the chip controls the future, and focusing entirely on mathematics and software. Huawei founder Ren Zhengfei seems to capture this perfectly.
His perspective crystallizes the new reality. He argued that there's no need to panic about the chip challenges because innovative methods, like those employed by DeepSeek, can produce comparable computational results. He made a powerful distinction between the physical and the abstract, saying, software is built on mathematical symbols, codes, and layers of cutting-edge algorithms. There are no shackles here.
That is profound. It implies that the hardware blockade is temporary and physical, but the software challenge is one of pure intellectual resourcefulness, a domain that cannot be restricted by trade policy.
He argued the real challenge lies in education and talent development, predicting that in the future, China will have hundreds or even thousands of operating systems supporting its progress across various industries. He underscores that without fundamental theoretical research, they lack roots. The DeepSeek technical report is evidence of that fundamental theoretical research bearing fruit.
This shift isn't only about high-end AI chips either. The restrictions are accelerating innovation across the entire semiconductor supply chain, even in less advanced areas, solidifying domestic supply security.
The trade policies are accelerating China's shift toward non-US chips, particularly in mature node semiconductors, meaning chip processing technology using 28 nanometers and above, used primarily in automotive and mid to low-end markets. Experts noted that these restrictions ironically catalyzed China's progress, driving upgrades in high-value upstream segments like lithography machines. Instead of simply mitigating export losses, Chinese firms were incentivized to focus heavily on domestic import substitution and self-sufficiency.
And we see massive corporate R&D commitments reinforcing this drive for domestic mastery. This isn't a small side project, it's a national focus.
Look at the commitment from a major tech player like Xiaomi, known primarily for consumer electronics. They unveiled their 3nm X-Ring 01 chip for smartphones, which was the result of over 4 years of intensive R&D. Furthermore, Xiaomi plans to invest a colossal 200 billion yuan, roughly $27.8 billion, in R&D between 2026 and 2030. Their chairman, Lei Jun, stated that if Xiaomi is to become a world-class hardcore technology company, mastering chip technology is a summit we must conquer. This is a battle we cannot avoid.
That level of financial commitment shows that the goal is complete technological self-reliance driven by necessity and the new economic reality established by these trade restrictions. So let's tie this back to the final product. The sophistication of the DeepSeek V3 model required not just efficient pre-training, but a highly complex post-training pipeline. Let's briefly review that, reinforcing the notion that this is a complete sovereign development stack from the foundational algorithms right up to the user alignment.
The entire development stack is highly sophisticated and meticulously refined. DeepSeek V3 started with that incredibly strong, cost-effective base model and then went through meticulous refinement. One key capability is its long context processing. After the initial pre-training, they used an extension technique called YARN to progressively expand the context window from 4K up to an enormous 128K tokens.
That is a massive context window, matching or exceeding most proprietary frontier models. Did it maintain consistent performance across that length?
Yes. The long context capability was rigorously validated using the needle in a haystack tests, which involve burying a specific fact deep inside a long document and asking the model to find it. DeepSeek V3 demonstrated consistent robustness across context window lengths up to 128K. This validates the success of their MLA memory compression strategy and context extension training pipeline.
Next, alignment. The model needed sophisticated refinement beyond just supervised fine-tuning to handle complex tasks like coding and math accurately.
They employed advanced reinforcement learning, utilizing a customized reward model. This included distillation from an internal DeepSeek R1 model, which significantly enhanced performance in challenging technical areas like math and coding. The RL approach was key to aligning the model more closely with human preferences and optimizing performance in domains where high-quality SFT data might be limited.
How successful was this RL alignment compared to closed-source models? This is often the area where open-source models lag behind.
Remarkably successful, especially in complex, open-ended tasks. On ArenaHard, a challenging benchmark focused on complex prompts, coding, and debugging, DeepSeek V3 achieved a groundbreaking win rate of over 85% against the GPT-4 baseline. This result performs on par with Claude Sonnet 3.5 and significantly bridges the performance gap between open-source and closed-source models in challenging domains. It also outperformed both open-source and closed-source models on AlpaCaval 2.0, showcasing outstanding proficiency in writing and straightforward question answering.
That suggests the model is not only technically capable, but also highly aligned and useful in subjective evaluations. They also mention a self-improvement loop, which sounds like the absolute cutting edge of alignment technique.
That is the self-rewarding paradigm. For general scenarios where hard-coded feedback is impractical, DeepSeek V3 utilized a method akin to constitutional AI. This means they leverage the model's own judgment ability. DeepSeek V3 achieves 87% on reward bench average, comparable to GPT-4o to generate its own feedback source.
The model literally judges its own responses and uses that evaluation to improve itself, bypassing the expensive and often biased human feedback loop.
Precisely. By integrating additional constitutional inputs, the model optimizes itself towards a desirable direction based on its own high-quality judgment. This self-improvement loop enhances alignment in subjective evaluations, demonstrating that the LLM can function as a versatile processor, transforming unstructured information into rewards to facilitate its own self-improvement. It speaks to a highly advanced and replicable development pipeline that is sustainable and independent. The DeepSeek V3 story fundamentally changes the conversation about AI capability development globally. It proves that the multi-billion-dollar hardware moat designed to stop progress is, in fact, porous, and that the core of AI competition is decisively shifting. The actual battleground is moving away from computational brute force toward mathematical ingenuity and software optimization. DeepSeek V3 demonstrated that exceptional computational power can be manufactured through extreme efficiency co-designed with available hardware, rather than requiring the unchecked purchasing of the latest, most restricted components. This development establishes a sustainable and replicable model for emerging markets globally to build sovereign intelligence capabilities, providing a direct circumvention of international trade restrictions entirely through superior engineering and algorithmic design.